Welcome! In this session, we'll explore a fascinating problem from LeetCode, titled Smallest Index with Equal Value. We'll understand the problem requirements, discuss potential approaches, and evaluate their efficiency. Let's dive in and get started. In this problem, you're given a zero-indexed integer array called nums, and your goal is to find the smallest index I in the array that satisfies a specific condition. The condition is that I% should be equal to nums, I. Here, I% means the remainder when the index I is divided by 10. If such an index exists, you return that index. If no index meets the condition, you return -1. The input to this problem is the array nums, which has a length n. The output should be a single integer representing the smallest index that satisfies the condition, or -1 if no valid index is found. Let's look at the first example to better understand the problem. Suppose the input array is nums equals 0, 1, 2. The output in this case is 0. Why? Let's check each index. For I equals 0, we calculate 0% 10, which is 0. This matches nums, 0, which is also 0. For I equals 1, 1% 10 is 1, and this matches nums, 1. For I equals 2, 2% 10 is 2, and this matches nums, 2. Since the condition is satisfied at multiple indices, we return the smallest valid index, which is 0. Now consider the second example, where the input array is nums equals 4, 3, 2, 1. Here, the output is 2. Let's check each index again. For I equals 0, 0% 10 equals 0, but nums, 0, is 4, so the condition is not met. For I equals 1, 1% 10 equals 1, but nums, 1, is 3, so again the condition is not satisfied. For I equals 2, 2% 10 equals 2, and this matches nums, 2, which is also 2. Therefore, the smallest valid index is 2. In the third example, the input array is nums equals 1, 2, 3, 4. Here, no index satisfies the condition. For all indices, the value of I% does not match the corresponding nums, I. As a result, we return -1. The constraints for this problem are as follows. The length of the array nums is between 1 and 100, and each element in the array is between 0 and 9. Let's also consider edge cases. For small arrays, such as nums equals 0, the output is 0, because 0% 10 equals 0. But for nums equals 1, the output is -1, because 0% 10 does not equal 1. For large arrays, the solution must handle arrays of up to 100 elements, like nums equals 9, 8, 0, and iterate through all indices to find the smallest valid one. If there's no valid index, such as in nums equals 9, 9, 9, the output is -1. Finally, if there are multiple valid indices, like in nums equals 0, 1, 2, the smallest index is returned, as required by the problem. To solve this problem, a natural starting point is the brute force approach. The intuition here is simple. Since we need to check a condition for every index in the array, we can directly iterate through the array and evaluate whether the condition I% equals nums, I, holds true for each index I. If we find an index where this condition is satisfied, we return that index immediately. If no such index exists after examining the entire array, we return -1. The steps are straightforward. First, loop through all indices from 0 to n1. For each index, check if the condition holds. If it does, return that index right away. Otherwise, complete the loop and return -1. The time complexity of this approach is O(n), as we only make a single pass through the array, and its space complexity is O(1), since we are not using any additional data structures. This makes the brute force method both simple and efficient for this problem. Now, let's consider an optimized approach that focuses on early exit. The key insight here is that the brute force method is already efficient, as we iterate through the array only once. However, we can emphasize early termination because we are guaranteed to return the first valid index, which will always be the smallest due to the sequential nature of our iteration. This ensures the solution is optimal. To implement this, we start iterating through the array from index 0. For each index, we check whether the condition I% equals nums, I, is satisfied. As soon as we find a match, we return that index immediately without any further checks. If we complete the loop without finding a match, we return -1. The time complexity remains O(n), but in the best-case scenario, the condition might be satisfied early, allowing us to exit the loop sooner. The space complexity also remains O(1), as we are not using any additional memory. By emphasizing early exit, we maintain simplicity while ensuring optimal performance. The chosen strategy for this problem builds directly on the brute force approach with early exit, as it balances simplicity, clarity, and efficiency. There are several reasons why this approach is ideal. First, the brute force method has linear time complexity and constant space usage, which are both optimal for this problem. Since the primary task is a simple condition check for each index, there are no significant optimizations beyond ensuring early termination. A key observation here is that the modulo operation I%10 simplifies the comparison by isolating the last digit of the index, making the computation straightforward and efficient. Additionally, because the problem guarantees that returning the first valid index ensures it is the smallest, there's no need for any additional data structures or sorting. Alternative strategies, such as sorting or hashing, would only add unnecessary complexity and increase the time or space requirements without any advantage. For example, sorting the indices would increase the time complexity to O(n) log n, and a hash map would consume extra space without improving performance. Recursive solutions are also unnecessary, as they introduce overhead and potential stack limitations. Thus, the simplicity of our chosen method makes it the most effective solution. Given these insights, the brute force approach with an emphasis on early exit stands out as the optimal strategy for this problem. Its simplicity ensures that the solution is easy to understand and implement, while its efficiency guarantees that the task is completed in minimal time. This method avoids unnecessary complexity, as the problem itself is already straightforward. The final trade-off here is clear: we prioritize clarity and readability without sacrificing performance. Since the problem doesn't demand advanced computations or elaborate data structures, there are no significant trade-offs to consider. Overall, this approach is a perfect match for the problem, achieving an optimal balance of simplicity, efficiency, and clarity. In this problem, we're tasked with finding the smallest index I in an array nums such that the condition I%10 equals nums I holds true. If no such index exists, we return -1. To tackle this, we can start with a straightforward brute force approach. The intuition behind it is simple: we iterate through each index in the array, calculate the value of I%10, and compare it to the value at nums I. If they match, we immediately return the current index since we're processing indices in order. If none of the indices satisfy the condition, we return -1. The steps are as follows: initialize a loop to iterate through the array, compute I% for each index, and compare it to nums I. If they are equal, return I, otherwise, move on to the next index. If the loop finishes without finding a match, return -1. Here's a simple Python implementation of this logic, which directly applies these steps. Now, let's break down some key insights about this approach. First, the modulus operation I% ensures that we are focusing only on the last digit of the index I. For example, if I is 12, the result of 12% is 2, which we then compare to nums 12. This makes the comparison straightforward and predictable. Additionally, the algorithm benefits from an early exit mechanism. If the condition is satisfied at any point, the loop terminates immediately, which can save computation when a match is found early. There are also important edge cases to consider. If the array is empty, the function will return -1 as the loop never runs. Similarly, if no index satisfies the condition, the algorithm will traverse the entire array before returning -1. For large arrays, the memory usage remains efficient, as the algorithm uses only a single loop variable and does not require any additional data structures. Let's analyze the complexity of this algorithm. The time complexity is O(n), where n is the length of the array. This is because the algorithm performs a single pass through the array, evaluating each element once. The space complexity is O(1), as we only use a loop variable and no additional memory beyond the input array. While the algorithm is efficient, there are possible optimizations to consider. For instance, if the array is guaranteed to contain only values between 0 and 9, we can limit the search to a maximum of 10 elements, since I% will only produce values in this range. Another optimization involves pre-processing the array to filter out values that cannot possibly satisfy the condition, such as negative numbers or values larger than 9. This can significantly reduce unnecessary checks for certain inputs. To illustrate, consider the example nums equals 0, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1. On the first iteration, I equals 0, and since 0% 10 equals 0 matches nums, 0 equals 0, the algorithm immediately returns 0. In another example, with the input nums equals 1, 2, 3, 4, 5, we see how the algorithm systematically processes each index. At I equals 0, 0% 10 equals 0 does not match nums, 0 equals 1. At I equals 1, 1% 10 equals 1 does not match nums, 1 equals 2. This continues for all indices in the array, and since no index satisfies the condition, the algorithm returns -1. This example highlights the thoroughness of the brute force approach, as every index is checked in order. In summary, while the brute force method is simple and effective for this problem, it can be further optimized for specific scenarios, such as constrained inputs. Nonetheless, the algorithm's efficiency is already sufficient for most cases due to its single-pass nature and minimal space requirements. In this solution, we aim to find the smallest index I in the array nums such that the condition I%10 equals nums, I, is satisfied. If no such index exists, we return -1. Here's the step-by-step explanation of the code. 1. Class definition. We define a class solution containing the method smallest equal to solve the problem. This aligns with the format required by LeetCode. 2. Iterate through the array. Using Python's enumerate function, we loop through each element in the array nums along with its index. Enumerate provides a tuple, I, number, for every element, where I is the index, and number is the value at that index. 3. Condition check. For each index and value, we check if the condition I%10 equals number is satisfied. This means the remainder of I divided by 10 matches the value at index I. 4. Return the first match. If the condition is satisfied for any index, we immediately return that index. This ensures we find the smallest such index since we're iterating from the beginning of the list. 5. Handle no matches. If the loop completes without finding any index that satisfies the condition, we return -1. This is the required output when no valid index exists. The solution is efficient with a time complexity of O, n, where n is the length of the array nums. This is because we only need a single pass through the array. The space complexity is O, 1, since no additional data structures are used. This is the Java implementation of the smallest index with equal value problem, LeetCode number 2057. The logic mirrors the Python solution, iterating through the array to find the first index where the value equals the index modulo 10. Key differences include Java-specific syntax, such as type declarations, e.g., int, for arrays, and the absence of Python's enumerate function. The solution is concise and adheres to Java conventions. To solve this problem, we start by examining example 1 where the input array is nums equals 0, 1, 2. The goal is to find the smallest index, I, such that I%10 is equal to nums, I. First, we initialize the iteration process, where we loop through each index I and its corresponding value, number, in the array. In the first iteration, I is 0, and number is also 0. We check the condition 0%10 equals 0, which evaluates to true. Since the condition is satisfied, we immediately return I equals 0 as the output. This gives us the final result for this example, where the first index satisfying the condition is 0. Now let's look at example 2 with the input array nums equals 4, 3, 2, 1. Again, we iterate through each index I and its corresponding value, number, checking if the condition I%10 equals nums, I, holds. In the first iteration, I is 0, and number is 4. The condition 0%10 equals 4 evaluates to false, so we move to the next index. In the second iteration, I is 1, and number is 3. The condition 1%10 equals 3 is also false. In the third iteration, I is 2, and number is 2. Here, the condition 2%10 equals 2 evaluates to true, so we return I equals 2 as the output. The smallest index that satisfies the condition in this example is 2. Next, we have example 3 with the input array nums equals 1, 2, 3, 4, 5. As before, we iterate through each index I and its corresponding value, number, to check if I%10 equals nums, I. In the first iteration, I is 0, and number is 1. The condition 0%10 equals 1 evaluates to false. In the second iteration, I is 1, and number is 2. Again, the condition 1%10 equals 2 is false. This pattern continues as we check I equals 2 with number equals 3, I equals 3 with number equals 4, and I equals 4 with number equals 5. In all cases, the condition does not hold. Since no index satisfies the condition, we conclude this example without finding a match. For example 3, since no index satisfies the condition, we return -1 as the final output. Now, let's reflect on some key observations about the solution. The condition I%10 equals nums, I, ensures we are specifically looking for indices where the value matches the last digit of the index. The algorithm stops at the first match because the problem explicitly asks for the smallest index. If no match is found throughout the array, the algorithm returns -1. This approach is efficient, with a time complexity of O(n), as we only iterate through the array once. Additionally, the space complexity is O(1), as no extra data structures are required for the solution. To analyze the time complexity of this algorithm, let's start by considering its structure. The algorithm iterates through the input array nums using a single for loop. This loop runs from index I equals 0 to I equals n1, where n is the size of the array. Because each element is visited exactly once, the number of iterations is proportional to the size of the array, giving us a time complexity of O(n). Within each iteration, the algorithm performs two constant time operations, a modulo operation, I%10, and an equality check, I%10 equals nums, I. Both operations are O(1). Additionally, if a match is found, the algorithm immediately returns the index and stops. This means that in the best-case scenario, where the first element satisfies the condition, the algorithm terminates in O(1). However, in the worst-case scenario, where no match is found, the loop runs to completion, resulting in O(n). Combining all these steps, the overall time complexity of the algorithm in the worst case is O(n). Now let's discuss space complexity. This algorithm uses a constant amount of extra memory, regardless of the size of the input array. It does not create new data structures or allocate additional space based on the input size. The input array nums is used as it is, without being modified or copied, so no extra storage is required for input handling. The variables used in the algorithm, such as in number from the enumerate function, as well as the return value, all require a fixed amount of memory. Because the memory usage remains constant and does not scale with the size of the array, the space complexity of the algorithm is O(1). This efficient use of memory makes the solution highly space-optimized. Let's compare the current solution to a brute force approach. A naive implementation might involve using nested loops. The outer loop would iterate through the indices of the array, while the inner loop checks the condition I%10 equals nums, I. Although this would result in the same overall time complexity of O(n), it introduces unnecessary redundancy and is less elegant. The current approach, on the other hand, eliminates the need for nested loops by leveraging Python's enumerate function and exits early as soon as a match is found. Now consider the best, average, and worst-case scenarios for our algorithm. In the best case, the condition I%10 equals nums, I, is satisfied by the very first element, resulting in an O(1) runtime. In the average case, the condition is met around the midpoint of the array, which corresponds to approximately O(n)/2 operations. However, in big O notation, this simplifies to O(n). In the worst case, where no elements satisfy the condition, the algorithm must traverse the entire array, resulting in a time complexity of O(n). To mathematically confirm the big O analysis, let's break it down. The algorithm performs a single pass through the array, visiting each element exactly once. For an array of length n, the number of iterations is directly proportional to n. During each iteration, the operations performed, calculating the modulo, checking equality, and updating loop variables, are constant time, or O(1). As a result, the total time complexity is O(n). On the other hand, the the space complexity remains 1, because the algorithm does not allocate additional memory based on the input size. It only uses a constant amount of memory for the loop variables and the return value. This combination of linear time complexity and constant space complexity demonstrates that the algorithm is both time efficient and space efficient, making it an optimal solution for this problem. When solving this problem, there are several common mistakes to watch out for. First, forgetting to handle edge cases can lead to unexpected errors. For example, scenarios like an empty array, an array with just one element, or one where all elements are the same often reveal hidden bugs if not tested thoroughly. Ignoring these cases can result in incorrect outputs or even runtime errors. Another frequent mistake is misunderstanding the modulo condition. The problem specifies that the index modulo 10 must equal the value at that index, but some developers mistakenly flip this condition, comparing the value modulo 10 to the index instead. This subtle error can completely invalidate your solution. It's also critical to adhere to problem constraints. For instance, assuming values fall outside the given range can lead to undefined behavior or overly complex logic. Lastly, relying on inefficient brute force methods might seem tempting initially, but it's important to keep scalability in mind. Brute force approaches often fail to handle larger inputs efficiently, which can result in time limit exceeded errors. Addressing these pitfalls early on will save you time and frustration as you work through the problem. Another mistake to avoid is hard-coding solutions. Writing specific checks for a few cases might seem like a quick fix, but it fails to account for the generality required in coding challenges. This approach is not scalable and will break down when faced with inputs outside the hard-coded range. Now, when tackling array problems like this one, pattern recognition is key. Pay careful attention to the relationship between indices and values, as this often reveals underlying cyclic or periodic behavior. Recognizing such patterns can simplify the logic significantly. Optimization is another important consideration. If a condition allows you to skip unnecessary checks, such as directly accessing indices like nums, take advantage of it to improve efficiency. In interviews, always take the time to clarify constraints, such as the size of the input, valid value ranges, and edge cases. This step helps you avoid false assumptions that can lead to mistakes. Lastly, be ready to discuss the time complexity of your approach. While a brute force solution here might be identifying opportunities for optimization can make your solution stand out, especially if you can skip redundant checks or streamline your logic. This problem shares similarities with several other LeetCode challenges, such as find all numbers disappeared in an array or find all duplicates in an array. These problems also deal with identifying patterns in arrays, making them excellent practice for honing your skills. Now, in terms of alternative approaches, optimized iteration is one technique to consider. Instead of iterating through every index, you can look for patterns or constraints like periodicity or specific ranges that allow you to skip unnecessary checks. The trade-off here is that the logic becomes more intricate, but the runtime improves dramatically for larger inputs. Another option is pre-processing, where you use additional structures to mark indices or values, such as a hash map to record occurrences. While this approach often simplifies the main logic, it does come at the cost of increased space complexity, typically O(n). These alternatives can be powerful tools depending on the specific constraints and size of the input. For certain variations of this problem, binary search may also be an option. This applies if the array has properties like being sorted or monotonic, which allow you to reduce the solution's time complexity to O log n. Binary search can be a highly efficient technique, but it's more complex to implement and only works under specific conditions. It's worth considering when the problem hints at ordered or structured data, as it might save significant computation time. However, remember to weigh the trade-offs. While faster, the added complexity in implementation might not always be justified if simpler methods are sufficient. Great job! We've covered the problem's smallest index with equal value, analyzed approaches, and discussed key takeaways. Remember to keep practicing and refining your skills. Thank you for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!